So in the last video, we left off talking about how we can determine the velocity coming from a displacement graph. We had a bunch of different graphs, and we were able to figure out what each type of graph is basically kind of trying to convey. So the next question is, well, if taking the slope of a displacement graph gives us velocity, well then what would happen if I take the slope of a velocity graph? So displacement, slope, gives me velocity. Slope of that gives me what? Well, that's a good question. What type of measurements have we talked about? We talked about displacement, talked about velocity. The only other thing that makes sense would be the acceleration. Quick side note, there are actually other things past acceleration that we can take the slope of. And they have some terms too, except you would never deal with this in this class. But I'll just tell you now. So if you take the slope of acceleration, you get a jerk. If you take the slope of a jerk, you get a snap. Take the slope of snap, you get a crackle. And some of you may already know what comes next. When you take the slope of a crackle, you get a pop. Snap, crackle, pop. One of the few cases of scientists showing their nerdy side. All right. So I want you to try to look at these graphs. So these are now velocity versus time graphs. And I want you to try to describe the object's motion very similar to how we did the displacement one. Now I want to remind you, these are velocity graphs, not displacement graphs. Try to think about what is going on with the velocity and then come up with the description. All right, pause video, work on itself, and we'll go over in a second. All right, so for graph A, it starts at some velocity and it remains at that velocity this entire time. So this is an object that is moving with a constant speed. And I could also say it's moving away. I know this because it's a positive value. So if I gave this a number, this would probably be positive 50, let's say. So that positive tells me it's away. The fact that it has no slope, it means that it's constant. And the fact that it actually has a velocity to begin with means it's moving. So going back to what I said before, the displacement graph that looked like this represented an object that wasn't moving at all. Because again, no change in the displacement, all that meant was that your position didn't change. Here, now we're saying our velocity isn't changing. So we're still moving, we're just moving without changing our velocity. Graph B, again, we just try to describe what's going on. The velocity starts at 0 and then it's going up. So the velocity is increasing. So this is an increasing V. And it's also moving away. I can also say that this is an acceleration graph because it's going to be representing an object that's accelerating. Graph C, I could kind of do the same thing. So this is going to end up being decreasing. So it starts at some velocity and it goes down to 0. So it's a decreasing velocity graph. The thing is, it is still going to be moving away because even though the velocity is decreasing, it is still a positive velocity. So you're still moving away from something. It's just that you're now let go of the gas and you're coming to a stop. So this is still also accelerating, though we probably would get away with calling it deceleration. All right. So again, now we still have the same type of graphs. We still have a constant graph. We still have a linear graph like in graph B and C. But now that we change the axes to talk about velocity, it is now representing a different type of motion. So this is another thing that you need to know. You need to know how these graphs represent displacement measurements and how it's representing for velocity graphs. One of the things I highly recommend that you do is pull out flashcards. I said this before, I don't normally recommend flashcards because there's a lot of stuff in this class that isn't really memorization based. This is one of those few things where I actually would recommend that you make some flashcards, have a bunch of graphs on each one, and on the back of what type of motion it has. So, things like that, like constant velocity, moving away towards something. All right. Going back to here, actually, I just want to clarify one thing of how would these graphs look in order for you to be moving towards something. As we said, we would need the velocity to be negative. So if this is representing zero velocity, the graph would have to be in this section of the graph. So like looking like this or looking like this. If this is the first quadrant for math, this ends up being the fourth quadrant. All right. So we talked about how we could take the slope to go up in difficulty, going from displacement, velocity, and acceleration. I pretty much think of this as like climbing a ladder. Displacement is our basic type of measurement. The next step up is velocity, and then the next step up is acceleration. And we go up the ramp or up the ladder by taking slopes. Now the next question is there a way to go backwards? If I give you an acceleration graph, is it possible to get velocity? And if I give you a velocity graph, is it possible to get displacement? Now, those who take calculus or possibly pre-calculus may know what the opposite of slope is, but for those who don't know, the opposite is called the area. So this is where you take the graph, you turn it into a shape, and then you take the area underneath it in order to find the thing below it, to go backwards. All right, so try that for questions 6 and 7. So pay attention to the type of graph that we have and think about, are we going to get the information by reading it, taking the slope of it, or taking the area? Pause the video, work itself, and we'll go over in a second. All right, so we have a velocity graph. In order to get the distance, we have to take the area of a velocity graph. So this is one thing that I always mention. I say there are 3 things that you can do when you have a graph. You can either read it, take the slope of it, or take the area. You can only read it if what they're asking for is what's on the axes. So if this is a distance graph or a displacement graph and they ask you for distance, then you just read it. As far as slope and area, this is where you have to figure out. This is what you have to remember. Velocity graph, the slope of it is going to be meters per second squared, acceleration. So that means area would be distance. All right, so during the 6 seconds, I'm going to turn this into a shape. So I'm taking the area. I have a rectangle here. The area of a rectangle is going to be length times width. The length is going to be 2, because 4 minus 6. And the width, or in this case the height, is going to be 10. So this area is going to be 20. And then this area is the area of a triangle, which is half base times height. The base is 4, and the height is 10. So we end up getting 20 again. So what is the total distance? 20 plus 20 is 40. All right, going to question 7. They want to know what is the acceleration of the car at 5 seconds. So this is 5 seconds. If I look here, or if I think back to what I get, whether I'm going to read it, slope it, or area it, in order to find the acceleration, I want to take the slope. So the slope of this is what's going on in this line. Well, it starts at it starts at 10, stays at 10, and ends at 10. So no acceleration. So the acceleration is 0. Now, this is one of the reasons why I usually recommend that you don't just plug into an equation. Whenever you have a graph, I highly recommend that you never use any of the equations that we've gone over. You don't use v bar equals d over t. You don't use the acceleration, no magic d, none of it. You do one of these three things. Read it, slope it, or area. That's it. Because there are a lot of these little tiny caveats that you'll have to remember if you try to do an equation that'll make it so that you get it wrong. So going back to here, a very common thing that people would do is they would say, oh, well, acceleration is change in velocity over time. My velocity is 10, the time is 5 seconds, so the acceleration's 2. But this is completely wrong, mainly because of the fact that in here, the change in velocity, because remember, these are two different motions. The velocity goes from 10 right before 5 seconds to 10. So the change in velocity is 0, hence why the acceleration is 0. So there's all these really weird things that you have to kind of be aware of in order to actually use the equations. And because of that, 90% of the time you're going to get it wrong. So that's why I say do not ever use an equation on a graph, not, or at least not a motion graph. You either read it, slope it, or area. That's it. Alright, I'm going to pause the video here, and we'll end up continuing on and finishing up our discussion on motion graphs. Alright, if you have any questions, let me know. Otherwise, I'll see you later. Good luck and have a great day.